Hello, Trinity Tigers. Welcome to the Learning Together live webinar series. This is another of the lifelong learning initiatives presented by Trinity University's Office of Alumni Relations. And I'm Nathan Cohn, class of 1995, host of the Learning Together podcast series. So I hope you're already a subscriber of that. If you're not, you can find it on your Apple Podcasts and, of course, directly through the Trinity website and the alumni office. I work at Texas Public Radio here in San Antonio, and we often talk about public radio as being a place where curious minds are welcome, which is why I love hosting and listening to the podcast series and this webinar today as well. It's my pleasure to introduce today's webinar speaker, Dr. Mark Lewis, class of 1996. So we're overlapping each other a little bit here at Trinity. Ever since I was a child, I've been fascinated by space, and so I asked the Alumni Relations Office when I saw this topic come up if I could visit with Dr. Lewis today for the webinar conversation about the Cassini mission. Cassini was launched in 1997 and spent 13 of its years in space orbiting Saturn from 2004 to 2017, and that's what we'll be talking about today. Professor Lewis's personality is probably best summed up as a fun-loving geek. His interests and activities largely coincide with his teaching and research activities. He loves to code, he loves science, especially the physical sciences. Dr. Lewis's primary teaching and research interests include the area of large-scale numerical simulations, specifically of planetary ring systems. And before we begin our conversation today, remember that you are going to be able to ask your own questions during this webinar as well. Mark will be happy to answer them during the webinar. He's smiling, saying he's happy to answer them to the best of the ability. That's always the disclaimer. So, Mark, before we get into talking about the Cassini mission itself, I want to know where your love of space came from. Can you tell me?
So, like you, it came from when I was a kid. I remember I got an atlas, which of course you normally think of as a bunch of road maps, but the front page of this atlas had kind of a diagram of the solar system and all the stats about the planets and whatnot. And so in like third grade, I just memorized every stat about the planets from that page. I also had the luxury, I was able to go to Austin at that time had magnet elementary schools. And so I was able to go to an elementary school that had extra astronomy. It was a STEM magnet school. And so they had some astronomy lessons that I was able to take that were, helped to further my interest. And while, it kind of mixed physics and astronomy and computer science as I went on, by the time that I came here to Trinity, this doing numerical simulations of astronomical systems was just something that I was doing.
Cool. Well, at the outset, I mentioned that this Cassini mission was launched in 1997 and spent 13 years orbiting Saturn. But its original mission at Saturn wasn't supposed to last that long, was it?
Yeah, no. And this is kind of the way that NASA does things. You launch a mission, and it has been designed to last a certain period of time, but most of the time, they actually live longer. And then, assuming that NASA has the funding, they're able to extend the mission. And in the case of Cassini, they were able to do this twice to give us a much larger mission than the nominal mission, which had very significant benefits for the science. Part of this is because of where Saturn is, it takes Saturn 30 years to go around the sun. In some ways, an ideal situation would have been for Cassini to be there for 30 years, but that wasn't really going to be feasible. But we were still able to be there for about half of a Saturn year, which allowed us to see the Saturn and the Saturnian system in different seasons. That was significant for the science outcomes.
And because of the length of time that it was actually there, and because they had the funding, there's a pitch for NASA funding and public support of it for you. But because of that length of time, they were able to make the discoveries that we're going to be talking about today, about the moons of Titan and Enceladus that we'll be talking about. So there were some magical things that happened.
Yeah, there's a lot more science that was able to be done because they were able to stay there for about half of a Saturnian year. not only did it just give them more passes by each of the moons, more passes by the rings, it also gave them the chance. Turns out Titan also has seasons, and so they were able to see seasonal variations on Titan that they wouldn't have been able to if it was only active for the nominal mission.
So the two moons that we'll be talking about today, Titan and Enceladus, and we're also going to get into the ring system of Saturn as well. But I mean, Saturn has like 62 moons or something like that, right?
Yeah.
So what was it about these two particular moons that piqued the interest of NASA scientists? Titan, before we came on here, you mentioned that they had already were looking at, but Enceladus was a little bit of surprise. Were they actively looking in the moon system for surprises like we're going to be talking about, or?
Well, so I guess we're always looking for surprises somewhere, right?
Yeah, sure.
That's why
that's the point.
That's why you send out these missions, because you expect that they're going to discover something that you didn't know, and so prior to Cassini, a few spacecraft had done flybys, and most notably the Voyagers. So you had Pioneer, and then you had the two Voyagers did flybys of Saturn. And so we had some data about the Saturnian system from up close, but of course the technology was what was available for the Voyagers. And they were flybys, they weren't orbiters, which means that you just get a very short look at the system as you go through. And so in the case of Titan, we already knew that Titan was here. I'll throw up.
Yeah, let's get into it.
So this used to be the background I would keep on my computer when I was in grad school. It shows kind of a number of the moons, I would say the larger moons, but the ones down inside are actually very tiny. And the ring system of Saturn. And so Titan was known to be the largest moon, but it's also
bigger than Mercury, right?
It is bigger than Mercury. It's the second largest moon in the solar system. Now, bigger radius-wise, not mass-wise. Mercury is a very dense body, but whereas Titan is a much lower density body. But it's the only moon that has an atmosphere, and unlike Venus, which also has a very thick atmosphere, Venus's atmosphere is primarily carbon dioxide, and so it's rather different. Titan's atmosphere is mostly nitrogen, just like the Earth's atmosphere, and so we knew that going into this, and so that automatically made Titan an interesting point to look at. Perhaps people thought that Enceladus would be interesting. It's inside of the E-ring. We now know it's the reason for the E-ring, and it's bright and shiny. It reflects a lot of the light that hits it.
Let me just interject to say, for those who don't know what E-ring is, you're basically labeling the rings going inside out.
And
right?
so on the bottom part of this figure here, it's actually not from outside inside out. It's order of discovery.
Oh, really?
Okay, yes. And so the original four rings that have been known for a very long time were labeled from the outside in, A, B, C, and D. And so those were kind of the main rings of Saturn. And then everything after that was when it was found. And so the E ring was next, and it's a diffuse ring that's really best seen if you go to the opposite side and look backward. The F ring is a very narrow ring. And then the G ring is also a somewhat narrow ring that's also more dusty.
Okay, sorry to interject.
And so Enceladus seemed like it might have some interesting stuff about it, but no one was expecting what we actually found there.
Yeah. So on Titan, one of our reporters at Texas Public Radio, Paul Flav, had been in conversation with Hunter Waite at Southwest Research Institute over the years, and he's followed the Cassini mission, our reporter, through Hunter over there, and Hunter was talking about how on Titan that they found what he called the largest organic compound factory in the solar system. Is that what does that mean? I'm
actually, I might disagree with Hunter on this one.
Go ahead.
But at least in a terrestrial sense. So I go there. You were talking about Titan's size. There's Titan compared to the moon and the Earth. It's a large body, and at least in Voyager images, that's what you see. And that is an organic haze. So it has this atmosphere, but we don't see any of the surface details when we look in visible light, because there's this organic organic molecules that are being formed in the atmosphere, and they're slowly raining out on the surface. The reason why I take issue with Hunter's take on that was technically similar things are happening in the atmospheres of Saturn and Jupiter, because they also have a lot of organic molecules and they're much larger.
Yes.
But at least as far as collecting it and accumulating it, all of that stuff is forming in the atmosphere, and then it's slowly raining out. And so the surface of Titan is kind of littered with hydrocarbons.
We're talking about like gases like methane and ethane?
Except not gases on Titan, because it's so cold. So the surface of Titan is 290 degrees Fahrenheit below zero. So you'd want a thick parka if you're going to go visit there. And under those conditions, methane and ethane are liquid.
Yes.
And then larger hydrocarbons that form there are solid powders that are down. Sure. So, like I said, we knew that this is going to be an interesting place because it has an atmosphere, and it has an atmosphere that's kind of Earth-like. But at least in the Voyager-style images, you get the picture that's on the left. These are actually 2 Cassini images. Now, in astronomy, when we make color images like this, the one on the left is actually a real color image, but the way they make it is they put in a blue filter, a green filter, and a red filter, take 3 separate photos, and then combine that into one. So it's not like the camera that you carry around with you that has different parts of the sensor that read red, green, and blue for a single shot. The light detecting elements that they have in here are kind of a single grayscale, but they put filters in. The one that's on the right, they replaced the red with infrared. And so if you look in the infrared, you can actually start to see details that are on the surface. Now, Cassini actually had 12 different scientific instruments for measuring things. And then the ones that go best in a slideshow are from the imaging. So it's photographs that are great. But we get so much more science from other parts of the spectrum. So there is an ultraviolet imaging spectrometer, there is an infrared spectrometer, there's a visible spectrometer, there were radio instruments, and then there's a slew of instruments that were measuring waves and particles. So they would dust detectors, and those were actually significant, not so much at Titan, but at Enceladus for actually detecting the stuff that was spewing off. This right here is Titan as kind of, I'll say, seen by the radio instruments. So the radio instruments can look right through the atmosphere and actually give you a measurement of what's happening on the surface. And it looks kind of weird because the radio instrument doesn't get a large scale. It takes an image of a track every time it goes over. And so you have this combination of different tracks that they did. And off on the kind of the right side here, these are lakes of methane. This is the North Pole of Titan. And as I said, they saw seasonal variations. So it's an interesting world. The surface would be challenging to live on for any form of life. And if you did, its chemistry would be really odd. Here on Earth, water is our primary solvent, which is a polar molecule, and so the chemistry of life on Earth is kind of dictated by the fact that water is our primary solvent. If you had something trying to live on the surface of Titan, not only does it have to deal with being 290 degrees below 0 Fahrenheit, but it has to deal with the fact that the primary solvent there is a non-polar molecule like methane. And so it'd be a completely different form. I think I'm going to go past that one. The other thing that makes Titan interesting, and this is something we didn't know until Cassini, is that there is inevitably a global ocean. So being so cold, water is, of course, at the surface just frozen. On the surface of Titan, water acts like rock. It's frozen, remarkably solid. But underneath that, there is, based upon the measurements that we got from Cassini, there's an ocean. Okay, that's liquid water, probably mixed with ammonia to prevent it from freezing, and it's under significant pressure. And those are the types of environments that seem likely to have simple life in them, much like how we think that a lot of the early life on the Earth potentially formed at the bottom of the Earth's oceans, where you had these hot thermal vents that provide energy. It's possible you could sustain life, there. And once again, the slew of scientific instruments on Cassini was significant for this, because the discovery of the ocean, we didn't take a picture of this. We have no way of seeing this. This is under kilometers of ice. This actually comes from things like the magnetic field measurements, the way that it alters the magnetic field lines that go around there. Also measuring the motion of the surface. So because the radar gives you a high accuracy for elevation, they actually saw Titan flexing. Okay, and so much like the moon raises tides on the Earth. We're all familiar with this. In some ways, the Earth flexes mostly in the form of the oceans rising and falling. This happens all through the solar system when you have two large bodies that are going around each other. In the case of the moon is tidally locked, so the same side always faces the Earth. That happens for pretty much all moons that are in reasonably close to their planets. But Titan's orbit isn't completely circular. It's going a little faster at sometimes, a little slower at sometimes. And so the side that's facing Saturn wobbles a little bit, and as it does, you get some expansion and contraction. And we were able to measure that.
And that's how they were able to notice that there's the liquid.
Yes, because the surface ice clearly has to be decoupled from the solid down underneath to allow it to flex that much.
So how is the liquid possible then underneath that?
Well, so you need. So as I mentioned, the fact that if you throw in some ammonia, water can go a lot lower in temperature before it freezes, and so that's a likely component. I don't think there is, and I'm sure that the people who support different theories for what's giving you your energy source here would like to contest this. We don't have as clear a picture of where the energy source is coming to keep this melted on Titan as we do on, say, Enceladus. It's possible that some of it is residual heat because Titan's fairly large. It could have just enough radioactive decay and residual heat inside of it to maintain this layer, especially with the ammonia mixed in there.
Powering itself almost.
Exactly.
Yeah.
Which is, so the thermal vents on the Earth are powered by radioactive decay happening down inside of the Earth, and that generates heat, which keeps the core molten. And you could have a similar, though smaller scale, source of heat here that's giving you just enough energy to keep it in a liquid form.
And so if there is any sort of single-celled or life form under, you need that in order to
provide energy.
Provide energy. We were talking about before we came on today about it being the heat for the soup in order to make it happen.
And so on Earth, at least at this point, most of the energy for life comes from photosynthesis.
Sure.
But Saturn is 10 times further from the sun, and the amount of energy you receive from a light source goes down as the distance squared. So the amount of sunlight, the energy that you could collect is down by a factor of 100. This is also one of the reasons why you don't see big solar panels on the Cassini mission. They would have had to be truly enormous,
humongous,
solar panels, like football field size solar panels, in order to power the probe. Instead, it used what's called a radiothermal isotope generator. So it had a little nugget of radioactive plutonium that decays quickly and produces enough heat that they can generate power from it.
Yeah. Well, let's go on in here.
So this is just artist rendition of the different layers that you have on Titan. A silicate core. And inevitably some high pressure ice outside of that, but then an ocean that seems to be global all the way around, with more ice on top of that, and the surface layer, which is organics. When the Huygens probe went down, you found different areas. There are highlands and lowlands, and the lowlands of Titan appear to have dunes in them, but they're not dunes of the sand, the silicate stuff we're used to. It's this organic stuff that's being produced and raining out of the atmosphere. And there's enough wind, because it does have a thick atmosphere on Titan, that they even saw dust storms. Once again, I can't call them a sandstorm, but dust, but it's of organic molecules that are in these dunes that can occasionally be blown around.
Pond scum floating through the air.
Exactly. I don't think I would recommend Titan as a place to visit, but scientifically it's definitely a very cool destination.
Well, let's move on and talk about Enceladus here.
So the real surprise of the Cassini mission was Enceladus. The general expectation for small moons, Enceladus is quite small, is that they're geologically dead, because they're small enough. Any radioactive decay that would have warmed them has passed. They've lost all of that. So it's challenging potentially to find a heat source for them. And once they become geologically inactive, they can freeze all the way through, and it's hard to undo that. So Enceladus is interesting because it's an icy body. It's very bright ice. That was something that we knew. It has what we refer to as a high albedo. It reflects a large amount of the light that strikes it from the sun. And here again, to give scale, okay, so whereas Titan is larger than our moon, Enceladus is smaller than Great Britain. So this is not a very large body. But on the bottom of Enceladus here, they've added some false coloring for these features that are called tiger stripes. And when we got there, what we saw is these tiger stripes actually have plumes of material that's coming out of them.
They're cracks.
They're cracks, and there's geysers that are shooting icy water out of this. And here again, the other instruments of Cassini come into play, because they were able to have Cassini fly through those geysers and if you will, taste the material that's coming out of there, measure the size of the particles, measure their composition, stuff like that. It's primarily water ice, and with organics mixed in. Once again, this isn't a huge surprise. Turns out when you look at the things that everything in the universe is made out of, these are common things to have around. But in order to have a geyser like this, it seemed very likely that, once again, liquid water. So much of the search in terms of astrobiology, is related to finding liquid water, because that's the life we understand. We know how that would work, because of what we've seen on the Earth. And so as soon as this was found, it's like, okay, there's probably something there. And then there was lots of discussion and lots of modeling about what this is. Here's another instrument. So instead of looking at this in the visible, you have the visible picture, which is just taken by the normal camera imaging system, but that the red, orange, yellow on there, which looks like a heat map, because that's what it is. That was actually from the infrared spectrometer, which was able to do mapping on Enceladus. And so these bands, what we refer to as the tiger stripes, not only do they have this water shooting out of them, they're warmer than the surrounding area. And once people have been, since Cassini was there a long time, people have been able to play with this. They were able to make multiple passes, do multiple measurements, and the current model of Enceladus in some ways is similar to the one of Titan. You have an ice crust over the top, and then you likely have a global ocean. This was one of the things that it took. We're talking about what you can learn by having more time there, by Cassini staying at Saturn longer. Was this debate, is this a global ocean or is this a localized ocean? And the evidence currently seems to point to this is a global
all over
ocean. And there's still this question of, okay, but what is powering this? Because turns out, so the moon just interior to Enceladus is Mimas, which is one of my favorite moons, in part because it looks like the Death Star, and in part because it actually plays a big role for the rings. So this is Mimas, which is a little bit closer to Saturn than Enceladus. They're not too dissimilar in size. But this is a geologically dead, rocky world. It's cratered.
Yeah.
There's nothing that interesting there, whereas the surface of Enceladus is dynamic, and there are almost no craters that you see in a lot of this terrain. And that's because it's constantly being resurfaced. The water that gets shot out of these geysers lands and covers up. So any small craters that you would form fill in on a fairly short time scale.
Do we know the difference in ages between those two moons, between Mimas and Enceladus?
0.
0.
There's probably some debate. So it turns out when you get to the rings, the question of the age of the rings is I think there's still some debate over that. But moons in general are primordial.
Yeah.
So they formed close to the beginning of the solar system 4.5 billion years ago. And so we need a heat source here, okay? Because it's small, it's not radioactive. This is one of these places, there's this significant aspect when you talk about planetary dynamics, which is what I do, things called resonances. And when I teach astronomy, the way that I try to explain resonances to students is imagine you're pushing a kid on a swing. Turns out when we push kids on swings, at least as adults, we always do it in a resonant way. Kid comes up, we give him a push. And then nothing pushes them until they get back up, and then we give them a push. But I'm sure you've seen children playing around with each other who push each other on the swing at random times. That's a non-resonant interaction. And resonances matter because gravity really isn't all that strong. And so unless the pushes add up, they don't do much. Turns out that Enceladus is in a 2-to-1 mean motion resonance with a moon just a little bit further out called Dione. Dione is a bit bigger. And what that 2-to-1 resonance means is that every time Enceladus goes around the moon or goes around Saturn twice, Dione goes around once. So like the kid on the swing, every time Enceladus gets back to here a second time, Dione is right there to give it a kick. Okay, and so it's small nudges, but they always add up because they're at the same place. As a result, Enceladus's orbit isn't quite circular. It's a bit elliptical. And we're talking about how Titan flexes because of its the elliptical nature of its orbit. Enceladus does the same. Okay, and so this tidal forcing is what actually gives you the extra heat. And in some ways, this isn't too surprising. The other moon that we know of in the solar system that has an ocean is Europa.
Yeah.
And in the Jovian system, you have Io, Europa, and Ganymede, and all three of those are in 2-to-1 mean motion resonances. So Io goes around twice every time Europa goes around once, and Europa goes around twice every time Ganymede goes around once. And that keeps them all on somewhat eccentric orbits. In the case of Io, there's so much energy from this that it's volcanic and it's spewing out stuff constantly. You don't even get the nice ices on top. For Europa, it's just the right amount of energy to keep a melted ocean, and it appears that Enceladus is similar.
Yeah, the reason I asked about the age a moment ago, which is fascinating that, and you're explaining it with the resonances here, is that the two bodies that are so close to one another could be so different.
Yes.
But one is in part basically kind of powering the other in a way.
Well, no, but
not
or
powering,
there's a third body.
Yeah,
that's
yeah,
powering.
the third body. Yeah.
So basically, Mimas has no one giving it kicks.
That's right.
And if it were in the right position with another moon to be getting these kicks, then who knows? Mimas could have an interesting geology.
Could have had a different story.
That's right. But it doesn't. And Enceladus got that instead. And so there are still interesting questions. Could this support life? Right. And how would we know? So on that NASA funding, going back to see these, there's already plans for a Europa mission. There is some evidence, and in fact, it came from here in San Antonio, Southwest Research. Kurt Rutherford is one of the scientists who discovered that that there actually probably are some plumes like this occasionally at Europa. But at Enceladus, they're going all the time.
So should we be looking there instead of Europa?
There are definitely some people who would argue for that, and in part because it's potentially easier to look. We know exactly where to go. People joke instead of, because there's these missions, these ideas that at Europa you go and you drill down through the ice or do something. Actually, probably as opposed to drill, you very slowly melt your way down through the ice. If you have a heat source, you just stay there, and over time you'll fall down through the ice. We joke that all you have to do at Enceladus is go through and catch the fishes that are being thrown out, these geysers, because you have these geysers that are throwing material out. It's probably not fish, but if you have single-celled organisms, small organisms that were living in this ocean, some of them should potentially be thrown out in these geysers, and so if you sent the right instrument to pass through the geysers, you would have a chance of detecting them. So yes, for further missions, and there are definitely people working on the instruments and what those missions would look like.
Wow. So the ring system of Saturn. Let's move on.
Yeah. So that's
this is where your heart lies.
This is where my true love is. So I consider myself a ring dynamicist. This is a lovely picture of Saturn, taken late in the mission because we're up high. So for most of the mission, Cassini orbited largely in the plane of the rings and the moons. Pretty much everything stays in a single plane. But towards the end of the mission, before they had it plunge into Saturn, they went up to a more polar orbit, which allowed them to get
gorgeous
angles.
shots like this.
Yes, exactly. Yeah. So you can get this, and superimposed on that is the results of what's called an occultation measurement. So once again, for science, we like to measure things in lots of different ways, and while the imaging makes the cool pictures, to understand things, we like to have other measurements. And so in the case of rings, it's very helpful to see how much light the rings block. And so one of the things that happened many times during the Cassini mission was different instruments, generally the imaging spectrometers, would be locked on a star. And they would watch that star as it passed behind the ring material. And they would measure how much light came through. And that allows us to have very high accuracy measurements of the amount of material that are in different parts of the rings. And so that little white line there is a measure of how much material is in different parts of the ring based upon how much light was blocked.
And the rings are made up of what, like 90% water?
Yeah, they're primarily water ice, and there's different amounts of contaminant. Turns out the inner C ring, which has a very small amount of material, is the most contaminated. Has the most things other than water ice in it.
So the rings themselves also, they're not like static, No. And there's things from the rings falling into the planet itself.
Yeah, so in fact the D ring, which is interior to the sea, is down in a point where it's kind of constantly raining onto the surface of Saturn. For its final passes, Cassini actually went through the D ring, and we worried about this because Cassini's moving really fast, and it turns out that hitting particles at really high speed does bad things to electronics or other elements. And so when they were going through the ring plane in close to the planet, they would orient Cassini so that it was leading with its antenna, kind of as a
shield.
As a shield, to go through so that it could take some of the dust hits and hopefully not be too bad. But there was always this fear, what if you hit a meter-sized body? No more Cassini. That'll be a quick end to the mission before we intended it. But it went through just fine. It was able to take great pictures and also do other measurements of one of the biggest ones from my standpoint at the end of the mission was to measure the mass of Saturn's rings. So by passing inside of the rings, and also having measurements where you passed outside of the rings, you can take the difference between how the spacecraft was accelerated on those two and get an estimate for the mass. And this is, this debate over how old the rings are. The kind of the standard logic that people have applied has been that if the rings were really massive, they had to be old, and if they were low mass, they had to be young. Not everyone completely agrees with that, but what Cassini found is that they're actually fairly low mass. And so it's possible that the rings are not primordial, that they have not been there since the beginning of the solar system and when Saturn formed. I do think there's still some debate on there. There's some dynamical arguments that one can make that say, no, this could still be primordial. And part of the argument for why they would need to be young if they're low mass is because, as you said, they're water ice.
Yeah.
But they're constantly having stuff rain down on them that's not water ice. Just like when you go out in the night sky and you see a shooting star. Okay, that was some chunk of material from the beginning of the solar system streaking through the Earth's atmosphere, getting really hot and lighting up. Well, that happens everywhere, and so you have these micrometeorite bombardments, and those micrometeorites aren't necessarily water. And so those are the contaminants. And if that's been happening for 4.5 billion years, things should start to get a little bit dirty, is part of the argument for the young rings, because they look new and fresh. Okay, that there's this argument that if they don't have enough mass in them and they've been getting bombarded, that implies they would have to be young to look the way they do. Like I said, I'm not certain that's a closed debate, but there at least is some consensus that seems to be the leading model right now.
I want to go back to something you said about the D ring raining into the planets.
Yeah.
So what is happening? What do we know about what's happening with those particulates when they go into the atmosphere of Saturn?
Well, and if you were on the other side, if you could have a little spaceship or a balloon, blimp in Saturn, you'd have some really nice meteor showers.
Yeah, well.
It would almost probably be a constant meteor shower around that region.
Yeah.
But they burn up and become just part of the atmosphere of Saturn.
So, that's what I was getting at, is that, because as we know that Saturn is a gas giant, it's not like, Earth, but yet it still has an atmosphere that things burn up in as it goes in. It's not like it's just falling into a cloud of some sort,
I think that actually leads nicely. This is my favorite picture from the entire Cassini mission. And it probably needs a little bit of explanation. Turns out that the Death Star moon, Mimas, is visible.
That little
in
one
there.
right there?
Yes, that's Mimas. At the bottom you can see the rings, and you can see some gaps in the rings that I'll talk about a little bit more. But what I find so interesting about this is the color. That's not the color we think of Saturn being. Okay, that is, in this picture, Saturn looks blue. Okay, the blue planets that we think of are Uranus and Neptune. Okay, and that blue in the case of Uranus and Neptune comes from methane. Well, it turns out that Jupiter and Saturn have a lot of methane too. Saturn's color is kind of like Titan's color for a reason. You have these organic hazes that are being formed by the sunlight powering chemical reactions that form large organic molecules, and they give it that kind of yellowish haze. What you see in this is the northern, so this is when we first got there, the northern part of Saturn is actually being shaded by the rings. So it's not getting as much light, which means there isn't as much production of these chemicals. So you get to see the blue tinge of the methane from it, as opposed to the brownish that you get from those organic molecules. I also just love the way you can see the structure of the rings and the shadow across the planet. But it highlights how Saturn itself is a dynamic environment, because so in the southern summer, the northern hemisphere isn't just, and obviously it's getting less light because it's pointing away, but it's also getting less light because the rings are casting it in shadow all the time. And that actually changes the chemistry of what's going on at Saturn. during that time.
We have a question here, Jeff Ramsey, who just loves the photos that you've been sharing here, class of '81, and is wondering specifically with that polar shot that you showed a few moments ago. This one right here, where can he get a copy of that? And I mean, lots of these photos are NASA images.
Yes. So they're NASA images. Doing some web searching. Turns out the Cassini Imaging team, their website is called Cyclops, CICLOPS.org. And so they have a whole bunch of images from the entire mission that are there. It won't include this. This was given to me by another researcher, and I would be happy to share it with Jeff. He just sends me an email. And I'll send him a copy of this. This is actually, I got this from a researcher who was on the Cassini team, but he works with the ultraviolet imaging spectrometer, which is where the occultations come from.
Yeah.
And so it's combining the data from those two instruments.
Now, another thing about the rings that I don't know if people, when you look at Saturn, you can see there's these gaps in the rings. And so what causes those gaps in the rings? As I understand, you can see some little moons that are actually in the gaps of the rings that are causing them. Is that right?
So some of them. So they're caused by different things. So the biggest gap, which is called the Cassini Division, and it's the division between the A ring and the B ring. Here, I'll use a mouse pointer here. So this gap right in here, this is the Cassini Division. It's been known of for a long. It's actually visible from the Earth if you have a good enough telescope and good enough viewing. That gap is being caused by this guy.
Okay,
so it turns out, once again going back to resonances, while Mimas is not in a nice resonance with another moon right now, it's in a 2-to-1 resonance with that part of Saturn's rings. And so Mimas's perturbations in that 2-to-1 resonance prevent that area from having as much material. And it actually forms the outer edge of Saturn's B ring, which is where the majority of the mass is. Now the gaps that are outside of that are potentially caused by other things. So it's worth noting, I guess this is
if you play Sgt. Pepper with this, no, I'm sorry.
It looks remarkably like a record player, and though in some areas and not in others. I guess full disclaimer, Cassini paid for my grad school. We have to talk about our funding here. So when I was working on this, the Cassini mission was I had an advisor who was on the Cassini UViz team, and so the money from that paid for me to go to grad school. Once again, going back to the whole NASA funding, it also funds future scientists, right? This helps both NASA and NSF play a significant role in that. So most of my work in grad school was actually looking at this gap right here, which I guess if I were to go up to this image is that thin strip right in there. It's called the Inca Gap, and here in the Inca Gap is a little dot, is a moon named Pan. Now Pan was actually discovered in Voyager images a fair while after Voyager had passed. They noticed, so there are these wavy structures that you can see down on this edge here, and those are actually caused by Pan. They're what are referred to as moon wakes. So if you picture, when a boat's going through the water, it has this wake that goes out behind it. The dynamics here are a little bit different because due to Keplerian shear, so Kepler's laws, things that are closer in orbit faster than things that are further away. The stuff inside of Pan is moving faster, the stuff outside is moving slower. So whereas when you're on a boat, all the water is going behind you. When you're a moon in the ring, some of the material is going in front of you and some of it's going behind you. And Pan is big enough that it pulls on this material and causes there to be these waves set up, and you can see compression and rarefaction where interesting dynamics that go on in there. So Pan is the largest, what we refer to as a gap moon. And there's a nice picture of Pan where it turns out that ring material has been falling along its equator forever, and so it kind of looks like a UFO and has this ridge around it.
What's its size, diameter-wise, so roughly?
So 10-ish kilometers.
Wow.
Okay, so this is not a big body.
Yeah.
This is a fairly small body. but it's big enough that it opens a gap in the ring. And now in this image, you'll notice there's another gap out here. That's called the Keeler Gap. And it is maintained by a little moon that appears in this image called Daphnis. And these days, this is one of my favorite subjects for simulating. So Daphnis is more on the order of 5 kilometers. Okay, and actually the radius, 3.8 kilometer radius, and it is just big enough to open a gap, but not by much. And you can see the gap isn't much bigger than the moon there, and so it passes very close to the ring material, and you can really see how you get this scalloped edge as the ring material is pulled by the moon, but it's going on an orbit. And so I threw in, this is a simulation that I did of that system, where the computer, I put in a whole bunch of basically virtual particles that just obey the laws of physics and run around to try to reproduce the physics here. On the science side, computer simulations give us the ability to understand things because you can turn off some physics and turn it on and find out what actually is causing stuff to happen. So it's all these different elements that help us do the science to discover stuff.
Cool.
Then going down further, so this was also one of the interesting discoveries. There's these things called moonlets. Okay, so Daphnis had not been seen prior to Cassini. It was expected because there was a gap there, but no one had actually seen it until the Cassini mission got there, and we were able to see it in there. We've also found, so this is what's referred to as the propeller Balerio. They're called propellers for obvious reasons. They look kind of like an old airplane propeller, and they're named after some of the original aviators. So that was the naming scheme that was chosen. But there's a what we refer to as a moonlet, and this is when you say, how many moons does Saturn have? This is one of those, how do you define a moon, right? Because in some sense, every particle in the rings is a moon of Saturn, and then the number just becomes astronomically large.
100 million moons.
No, we need a lot more zeros.
Billion.
Yeah. So in this case, you have we call them a moonlet. We don't give them the full credit of being a moon, because they haven't been able to completely separate the ring material around them. They're big enough to open a gap for a little while, but then diffusion, the ring material basically closes up that gap before it comes back around. And this Balerio is the largest of these. So the estimate for this, because we can't actually resolve it, so we have to do calculations based upon the size of the propeller, because we can't actually see the moonlet Balerio there, but you can see the effects that it has. It's about 1 kilometer in size. But we also found, and in this image, you can see all these little streaks which actually have that same propeller shape. Those are smaller moonlets, down to tens of meters, hundreds of meters size, that form these structures in there. And this is one of the remaining mysteries. They only exist in certain areas. There are these bands that have a whole bunch of moonlets in them. In case anyone's interested, the other structure, the thing that makes this look really pretty, this is called a density wave. Going back to resonances, this is a resonance with one of the small moons. I don't happen to know exactly off the top of my head which one this is. If I had to guess, it's probably a resonance with Prometheus, which is one of the moons that's just outside the rings by the F ring. But these higher order, these resonances, they also mean motion resonances, but here the ring material would go around something like 43 times when Prometheus goes around 42 times. So they're off by 1, kind of like that 2 to 1, but much higher values for the number of times they go around. And this causes some interesting dynamics. You haven't asked me the question that you often get, why do people care about the rings, other than they're pretty, is that this actually gives us kind of a laboratory to understand how disks interact with particles in them. And the reason you would care about that beyond rings is we're just now getting to the point in the discovery of exoplanets and looking at exoplanet systems where we can see the disks around other stars that are forming. And those disks have planets or protoplanets embedded in them. And there are certain parallels between the dynamics of how you launch waves, for example, in rings, and how planets launch waves in the disks around other stars.
So the more we know about these rings, then the more it's going to teach us, clue us into what is happening with the exoplanets.
That's right.
As well, because we can draw parallels between them.
Exactly. Exactly.
So lastly, before we got 10 minutes left here on our webinar time, and again, if you have any questions, then be sure and type them in either on Facebook Live or on the webinar material itself, and we'll answer them here as best we can. And last thing I wanted to, we've been kind of going from the outside in, so to speak. So again, Saturn being the gas giant planet that it is, what do we know about the structure of the planet itself? And
so this is, I pulled up a picture because one of the other really cool discoveries is that Saturn has this hexagonal vortex on its North Pole. Why? Though we don't know that yet. There are lots of people working on the explanation for why you have that. Like Jupiter, it has these large storms, and Cassini did see some really cool storms that formed and actually went the entire way around the planet to kind of form a band. There are some challenges. We actually don't have, because as you said earlier, Saturn is not solid. Right? There is no solid surface in there, and so what seems like a fairly simple question: how quick does Saturn spin? Right? Okay. So on the Earth, it takes 1 day for the Earth to spin around. How fast does Saturn spin around? How long does that take? We don't know.
This is because things are varying.
Yes, and so part of it is it doesn't even have to all spin together. Right? Different parts of Saturn can be moving at different rates than others, and the standard way of measuring this is to look. So, for example, at Jupiter, also no solid material for us to measure, but you can measure the rotation rate of the magnetic field. But Jupiter's magnetic field is off axis with its spin axis, and so you can see how fast the magnetic field gets whipped around. And Saturn's magnetic field is very nicely aligned, and so you really can't use that as a measurement here. But one of the other remarkable things that Cassini did discover is that most of those waves that I was showing you, like that density wave, that was a wave that was caused by a reaction to a moon that's just outside. They found waves that are on the inner parts of Saturn's rings that aren't being caused by any moon. And it turns out they're being caused by stuff inside of Saturn. So if you picture waves on the ocean, right, except much larger scale, there are wave structures inside of Saturn at regions, not a solid surface, but where you go from one density to a different density, much like air and water on the Earth. And they are potentially non-uniform. It's not just a perfect circle. It's a little bit lopsided in some ways, and that causes it to excite waves in the rings that we can see. And so the rings themselves, the inner parts of the rings, wind up being almost probes where we can measure the internal structure of Saturn. And this is one of the things that actually wasn't discovered until late in the Cassini mission, and definitely people are still analyzing, looking at these waves and then trying to figure out what that means for the internal structure of Saturn. That's definitely ongoing work.
Well, speaking of, question from the audience is, are there any future missions planned for the Saturn system and its moons?
No. So at least not, NASA does not have these in place. There are people designing these. And so whether or not they ever get off the ground will depend upon NASA funding and how they decide to prioritize things. There is a contingent that really wants to go back and look at Enceladus more closely. And I, assuming that we don't have horrible things happen to NASA funding, my guess is that will happen in my lifetime. But it's not there's not an actual timeline drawn out for it at this point.
Yeah, that same person also asked the question about will there be an archive copy of this webinar, and of course, yes, there will be. You'll be able to find it very easily on Facebook Live, as well as through the Trinity University's archived webinar series. So don't worry, you'll be able to catch any of this that you want to catch again if you joined us late, or if you just want to go back and look at some of those images again, or hear something that Dr. Lewis said, then you'll be able to hear that again as well. So we have hope then for the future. I agree with you that I'd love for something to happen within our lifetime again. And Enceladus being a right place for discovery seems like it would be a good choice, for NASA to go back to.
Now, though I have to say, personally, we also have two large planets in our solar system that have only been visited once. Uranus and Neptune both only had a single Voyager go by them. And so this is the whole priorities.
But to use your analogy earlier, you might want to fish where the fish you think the fish might be, right?
Yes. Well, and but this depends upon what it is that you're trying, because we know in some ways Uranus and Neptune we know very little about. If you're going the astrobiology route and you want to try to find life, definitely Enceladus is an easy place to go looking. Also, you have the advantage, makes it even better than Jupiter. You can go to Europa. If you send something out to Saturn, a lot of the new missions that people are proposing have like microsatellite ideas to them. And so you could, if you send something out to Saturn, you can have part of it go to Titan and part of it go to Enceladus, and actually get more bang for your buck in that regard as well.
Good. Well, Dr. Lewis, thank you very much.
Thank you,
It's
Nathan.
really been a lot of fun and fascinating to learn and see all these images and learn about the amazing things that have been discovered by the Cassini mission today.
It's very nice being here. I enjoy talking about it. I love this stuff.
Well, thank you so much for joining us on today's webinar. The next webinar is scheduled for January 22nd, and it's on a very special topic celebrating 150 years of Trinity University. It's called Looking Back to the Future, Trinity University's first 150 years. It'll be a live conversation with Professor Emeritus Doug Brackenridge, author of Trinity History, A Tale of Three Cities, Education Professor Angela Bridenstine, 1991 class, who is also the co-chair of Trinity's 150th Anniversary Committee. She's going to be hosting the webinar with Dr. Brackenridge, and they'll address that question. Where did we come from? How did we get here? And I dare say they'll probably look to the future as well. So thank you very much for joining us today for this webinar. My name's Nathan Cohn. Appreciate you signing on and enjoying this with us.